Let's take a look at the LUT Color layer in ProRaster. I'm using ProRaster Premium. If you haven't already watched the image layer and the RGB layer videos, then you should do so. So a LUT Color layer has three components. There's a color component, then the intensity component, which does hill shading, and the opacity component, which you use for pixel level transparency modulation. So in this case, we're mapping from data to a color table in order to generate a color at each pixel. So whereas the image layer uses RGBA data, color data, and the red, green, blue algorithm layer uses probably data that is already spectral in nature, whether it comes from aerial photography or whether it comes from satellite multispectral. It's probably going to be spectral data that goes into that transform. In the LUT color layer, you can put any kind of data, and we expect you to put any kind of data into this transform in order to render it. So it might be terrain data, it might be bathymetry data, it might be magnetic data or gravitational data, it might be tree height, it might be population data, it can be anything. So the important thing to do is to define a data transform which maps from your data to color and into the color table. So let's get started. I'll just browse to a raster to acquire some data here. So perhaps some terrain data. Okay, so this is data that's that is LiDAR terrain. Of course, we can turn on the intensity layer and we still see some hill shading. I'll just turn that off for the time being. You select your field, you select your band, you select your time range. You can put in a data conditioning filter. In this case, you might have some bad data values in your raster, or you might have a range of values that you don't want to see. You can use the data conditioning filter to take them out of the raster before it gets rendered. But the most important information is here, where we specify the data transform and we specify the color table. So here's our color table. Click on it and it will bring up this selection dialog, and you can come down and choose any color table like Zavidus. So all of the color tables that you've linked to via the color table editor are all going to be listed in this table. Plasma. And here's our data transform. So the way this works is that we have a list of data transform types, and then when you select a type, you get a sublist of specific data transforms that are of that type. Now, data transforms come basically in two types. They can either be determined by the statistics of the raster that you're rendering, or they can be manually defined, completely manually defined by various parameters. So if, for example, I go into a linear transform and I select linear, then this is a statistical transform, and it's going to find the minimum and maximum values in the dataset, and it's going to stretch them linearly over this color table. Similarly, if I choose your equal area transform, this is using the histogram, and every color in the color table will get the same amount of number of pixels rendered. And that's purely a statistical transform. Go back to linear. You can see there are a bunch of others in this list, and it's similar for all of the other transforms. So we have a 1% clip, 5% clip, 10% clip. So again, this is a statistical transform. It's going to work out 10% of the data range and bring the clipping limits in at the top and the bottom by 10% of the data range. So if I do that, we'll see more blue and we'll see less yellow. going down here, we have 0.5% Q clip, 2%, 5% Q clip. So this is a quantile clip. So same kind of thing, it's going to clip off the top and the bottom, but this time it's going to find the, for example here, the 5% quantile. So it's using the histogram information to compute that quantile and set the clipping limits based on that quantile. And then finally down the bottom you'll see there's a linear manual clip. Now when I select that, I can put in the clipping range from the bottom to the top. So if I put in, 10 through to 100, then I'm going from this dark blue at 10 up to 100 at this light blue, and so you can see that the hills have all become very yellow because they're mostly above 100 meters. Now this is a completely manual transform, so there's no statistics being used anymore in this transformation. So going into, say, the equal area transformation, there's two. There's an equal area and then a stable equal area. They both do the same thing, but the stable equal area transformation will do a better job for data sets that are highly skewed or have outliers. The only disadvantage of the stable equal area is it's a little bit slower to render. Now with equal area transformations you get this control here which allows you to set a value between a 0 and 100. Now if I set this back to 0 or 1, then that gives me a linear transform. And so basically this is a percentage between linear and between fully equal area. So equal area often looks a little bit too enhanced, but if you dial it back a bit, say to 50% or something like that, it can improve the visual appearance of that transformation. Logarithmic transformation. Again, we have various options here. So a logarithmic transformation converts the data into log space, bearing in mind, of course, that negative values and 0 values in log space can't be computed. So it's a special transformation, and what you need to do is set the minimum positive value at which the transformation will cease being logarithmic and it will become linear. So if you set, say, here between plus or minus 10, so above 10 and below minus 10, it's going to be logarithmic, and of course the negative numbers, it's just going to make them positive before it does the log and then make them negative again. And but between plus and minus 10, it uses a linear transform to get past that 0 level where, of course, the mathematics blows up. So there's a variety of logarithmic transforms there where you can set that threshold level at different values. And again, there's a manual clip. Sigmoid transformation is quite a useful one, especially for multispectral data. Allows you to lighten and darken the data. So if you have a sigmoid transformation with a k value of 0, then you've effectively got a linear transformation. Again, this is a statistical transformation. It's going between the minimum and maximum values, but you can specify clipping and you can also specify the manual clip. Just have a look at ranges. So if we have 8 ranges, splits the data up into 8 different colors, and you can see that there's now only 8 colors being picked out of that color table. And so there's a bunch of different ranges that you can choose. Firstly, manual clips, so here we're going between 10 and 100, and we'll put in, say, 4 ranges, and so we get 4 colors between 10 and 100. We can choose, so ranges can either be assigned based on the data range or the The range boundaries can be computed via quantiles. So this is a bit like equal area, but with a limited number of colors. You can center those ranges about the mean value. You can center them about the median value or about the statistical mode. Or you can make those ranges one standard deviation wide and center them about the mean. So there's a variety of options there. Now this option, stored transform, this goes off into the stored transforms that you create via the data transform editor dialog. So down here we have the data transform editor dialog. You can create transforms in here. For example, we can create a logarithmic transform. In addition to setting that minimum threshold level, we can also set the base of the logarithm, which wasn't an option through the main dialog. So there's some additional capabilities in the data transform editor. With our clipping, we can set our bandpass clip in data values, in percentages, in percentiles. There are other more advanced options for clipping and various other things. In addition, there are statistics and histograms we looked at for certain rasters, so that's a useful thing. And in here we have all of the table options where you can create tables via a spreadsheet, type all the values in manually and set up your own transformation. So if you create one of those things, then they're going to appear in here under stored transforms. I should just actually mention this last one. In addition to deviations about the mean, there's the Jenks natural break transform. So this is a process that figures out, let's say, 8 natural breaks, figures out the best place to put them in your data to make a nice presentation. So going to those, back to the stored transforms. So here's the transforms that I've created manually. You can use those. Now, there's one other way to define a transform, and that is to use a color table. So there are some color tables that have a color data map included in them. So let's go into the color table editor. Go into this external folder where I have some color tables I've made myself. And I'll just edit this color table. So this is a color table that combines color as well as the data map into one table. So you can see the colors specified down here. And I've only specified some of the colors in the color table. There are 1024 colors in total, but I've only specified about 20 or so. And at each one of those colors, I've specified what the data value is going to be. So this deep blue is mapped to -50. So this is a sort of an atlas style color table where we have blues of various shades for bathymetry, data below 0, and then we have this greens and browns for data that's above 0 for terrain. And this count specifies how many colors are in between the first color and the next color, the next specified color. So there's 32 of these dark blue colors, and they're going to be interpolated in red, green, blue space from here to here. So there's actually 1024 colors, so it's come out of here. Now I can use that as a data transform. So I go to that external folder where I know that that color table is. I choose the color table. That's my transform. I also have to choose the color table from the color table selector to get the colors. So this is the one that I'm after. So now we have a completely sort of manual transformation that maps data to color. And so if you have any terrain raster, you can use this combination of a color table with any terrain raster, and you're going to get the same color visualization for the same data value, for the same RL. So let's have a look at clipping. So you can see that there's a clipping here, a range here, and there's a control down here that says invalid beyond clip limits, and at the moment I'm not invalidating. So let's put in a range, let's say from 0 to 25. Oops, 25. And then let's select a clip. So let's clip below the minimum and above the maximum. So now we're only seeing the data that's between 0 and 25 meters. And in my color table, I know that anything between sea level and 1 meter above sea level is going to be white. I think it's 1 meter, might have been 2. Maybe it was 2. 2 meters above sea level is white, and then it goes into the greens and so forth. And so now we're just seeing the areas of our terrain that are below 25 meters. We'll go to 10 meters. You can see here on in this particular area, this is LiDAR data. Let's turn on the intensity so we can see the streets and the individual houses. So all these houses are below 10 meters above sea level. These ones over here are more like 1 meter above sea level. These ones less than 1 meter above sea level. So that's your clipping. There are other options. You can just clip above the maximum. So now we're getting some data that's just below sea level. And there are various options there. Now I just want to demonstrate this transform raster source option. So I'll create a new algorithm, make a new lookup table algorithm. And I'm going to choose global DEM, so there's merit global DEM. And then I've got some other data for Denmark, this happens to be, which at very high resolution, LiDAR data. So it's 40 centimeter resolution, whereas this merit DEM is 90 meter resolution, approximately. So let's add in a LUT Color layer. And we'll go and get that Denmark data. I haven't got it as a raster source, so I'll just browse to it. 1 second. Digital terrain model 2019. So this is a 170 gigabyte raster, this particular one. So if I zoom in, so here's our merit data down here. And here's the boundary where we go into the 40 centimeter LiDAR data. Now you can see there's a big color difference. So what I can do is I can go into the Denmark color, go into the color page, and I can choose the raster transform source. So I'm going to use a statistical transform, but I'm going to base the statistics on a different raster. So I'll choose the global merit DEM raster. I'm going to use that for statistics. So then let's go into color and let's say use equal area. We'll set this one to equal area as well. Now when I zoom in, well, zoom out. So that's what it looks like. And zoom in on this boundary that we know is somewhere between, here between our high resolution LiDAR data and our other data. So there's the boundary. So we're seeing no difference in color between those boundaries anymore. I'll just show you one more thing. So in this case we have multiple layers, and we have the hill shading turned on in both layers. Now I might want to control that globally. So I go up to the algorithm level and go to the shadow page on the algorithm level. Turn on enable override. So now I'm controlling the shadow for both these layers from the top here. So let's bring it over here, bring this one over here, might bring it down a bit, say 30, a little bit less shadow, a little bit less specular highlight. So you might be happy with that, you think that's a bit of an improvement or whatever. Maybe even a bit less. And here we have our very high resolution data. And if you zoom right in on this Denmark data, you can see where they've driven the tractor along their fields and where the plough share marks are. So that's the lookup table color layer.